Hello, my name is Dr. KJ Berry, and the purpose of this video lecture is to present the concepts for parametric thinking and to talk about the advantages for engineers. Parametric thinking is the language of engineers. Recently, I had a student a couple years ago, and this student says that I do think that MEC 322 has enhanced my skills and abilities as a student and engineer because it has taught me to step back and to see the bigger picture through following and understanding universal and parametric concepts. The purpose of this lecture is to provide a demonstration of parametric thinking for the defined problem. We want to determine the parametric equation to model the torque and power for the rotating cylinder in terms of the relevant problem variables. As you can see that we have a cylinder that is rotating within an outer tank. There is a liquid in between the fixed outer tank and the rotating cylinder. The cylinder, of course, is going to rotate at a certain speed, omega. Omega is specified in terms of radians per minute. We have the length of the cylinder, we have the inside radius and the outside radius. The torque, of course, has to overcome the shear stress or drag in the small gap due to the fluid viscosity. And that is very important to understand the basic concepts of the problem, is that what is fundamentally driving our solution roadmap. And that is the understanding that the torque that we have to apply to rotate the cylinder inside of the outer diameter tank, the torque has to overcome the shear stress or drag in the small gap due to fluid viscosity. And we assume that there's a linear velocity in the gap and also neglecting the end effects for the cylinder. The first thing we have to do is to ask the question, what are we trying to find? We're trying to find the torque. And in any discipline, any class, the torque is always defined as a force times a distance. In a class in electrical engineering, even if you're studying electrostatic forces, it's the electrostatic force times the distance. In mechanical engineering, if you're studying classical physics, it's the mechanical force times a distance. In fluid mechanics, we're talking about the shearing force from the axis of rotation times the distance from the axis of rotation. So once we understand the fact that we're talking about the force of shear, well, what is the force of shear? The force of shear is the product of the shearing stress, and note that a shearing force is not the same thing as a shearing stress. The shearing force, of course, has units of newtons. A shearing stress has units of newtons per area or newtons per square meter. So the product of tau, which is the shearing stress times the area, gives us a shearing force times the distance from the axis of rotation. And so now we know that from the fundamental definition of shearing stress, it's the product of the fluid viscosity times the shear strain. In this case, it's mu times dV dr, where v sub t is the tangential velocity at the inner surface. So the torque is equal to mu times dV dr times the area. And the area is important. It's the contact area, the area that is in contact with the shearing surface, times, of course, now the moment arm, or the distance from the axis of rotation. And so the fluid contact area in this case, of course, is 2 pi times the inside radius times the length of the cylinder. So this gives us a roadmap that we are trying to follow to solve the problem. So we started at the top of the pyramid, asking ourselves, what are the fundamentals that are driving the solution to the problem? What are the fundamentals that I will use to create a roadmap that will help me solve this problem? And so, and finally, we talk about the torque. The torque parametric equation would be equal to the product of mu times the shearing strain, dV/TDR, times 2 pi r squared, r sub I squared, times the length of the cylinder. So first of all, let's look at how do we find the tangential velocity. So we know that the tangential velocity from physics 1 for a rotating body is equal to r omega. The linear velocity at the at the inside radius is equal to the product of simply r omega. If we look at the units of tangential velocity, we have r, which is in feet or meters, times omega, that is the angular velocity in terms of radians per second. And so you note that the units of tangential velocity, if defined in terms of r omega naught, is equal to feet per second or meters per second. So so we have to also look at the definition of the angular velocity in terms of radians per second. Our value of angular velocity was actually given in terms of the traditional units of RPM, which is revolutions per minute. So if we look at the conversion from radians per second omega naught to if we look at the conversion of RPM to radians per second, we see that we have omega naught is equal to omega in terms of RPMs or revolutions per minute times 2 pi radians per revolution times 1 minute per 60 seconds. So omega naught in terms of radians per second is equal to omega in terms of RPM, which is revolutions per minute, times 2 pi over 60. You note that this unit, that radians actually has no units. And so it's important to understand also that a revolution is not a radius, it's not a radian. So on occasion, sometimes students will get those three terms confused and will not be able to correctly solve the problem. But you must understand that a revolution is not a radius, it's not a radian. So it's important to understand the difference between those three terms. So let's also now look at the linear gap velocity. Our goal is to find the velocity distribution in the gap delta. I know that delta is the difference between R0 and R sub I, and I know that the value of R is bounded between the inside radius R sub I and the outside radius R naught. So we can define a velocity distribution in the gap as V sub R is equal to V sub T over delta times R0 minus R. And once again, where R is a variable. So how do we get that? Well, we know that if we look at this picture here, that at R is equal to R0, we know that it's the value of my velocity is 0 because it's a fixed boundary. We know that at R is equal to R sub I, that V has to be equal to my tangential velocity. So at V sub T of R is equal to R sub I, we would have V sub T times R0 minus Ri over delta, which of course, as you can see, that at R is equal to R sub I, this indeed gives us the tangential velocity at the inside radius. So we have a velocity profile. V sub T is my tangential velocity is equal to the radius times the angular velocity, as we talked about before, which is R sub I times omega naught. And so the final description here is that V sub R, or V sub t as a function of r is equal to the product of r0 times r naught divided by delta times r0 minus r. And if we look at the derivative to find our shear strain is defined as dVt dr is equal to minus r sub I times omega naught divided by r0 minus r sub I. And so you should go through it and make sure that you see that derivative. And the negative sign here is not a problem. It simply implies that the rotation opposes the shear stress or the fluid drag. So if we look at the final equation here, we note that the torque is going to vary as the cube of the radius. Note we have an Ri and an Ra squared. So a 2x increase in my radius results in an 8x increase in torque. In fact, it's even greater since as r sub I increases with a fixed value of r0, r0 minus ri will decrease, resulting in a smaller gap and pushing torque higher. So a smaller gap means that we have a higher stress and a higher drag force, and thus a higher torque. The parametric equation allows for an engineer to study the impact of torque on all system variables. It is more useful than obtaining a single value at a single operating point and not understanding how each variable will impact the system operations. And engineering today is about systems engineering and systems thinking. Engineers can now plot one variable against another and can consider trade-offs and system optimization. So here we have our roadmap equation that gives us that helps us understanding how torque is influenced by the relevant system variables. And we note that mu is our viscosity has units of Newton seconds per meter squared. We know that omega naught is omega in terms of RPM times 2 pi over 60. And we also know that the power it takes to turn that shaft is always equal to the force times velocity, which of course the force times Ri omega. R omega is my tangential velocity. But since force times distance is torque, so the power is equal to the torque times omega. And so we can always convert the torque in terms of foot-pounds force into horsepower, because I know that 1 horsepower is equal to 550 foot-pounds force per second. So, but let's just check to make sure that our units are indeed correct. I have my parametric equation in terms of torque, which has parameters of viscosity, Ri, R0, omega 0, and L. And so this is our road map equation. If I look at my units here, I would have mu has units of foot-pounds force second per foot squared. I have r sub I cube or foot cube times omega naught radian per second divided by r0 subtract r sub I has units of feet times 2 pi L, and this is the units of feet. And so therefore we see that indeed that our units turn out to be foot-pounds. Cancel, and our units here indeed turns out to be foot-pounds. And so now I'm pleased. I'm happy. I know that my problem formulation has the right form, and it has the right units attached to my form. So when I present my solution to my team members, when I present my solution to my boss, um, um, I can provide confidence that my analysis and my approach is indeed correct and appropriate. So, um, in summary, here uh, we 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 understand that that the power uh, uh, that we're trying to determine the power to size uh, the motor. That's why we need to find power to understand the size of the motor necessary to turn that shaft. So we know that the power of the required motor varies by the cube of the radius and by the square of the angular velocity. So note that the power varies as a function of the cube, function of the cube of the radius and the square of the angular velocity. It is very important to know the power versus speed, which governs the system energy consumption and the overall system electrical efficiency. So the increased power consumption versus speed may also be important in considering the thermal heating with speed, as the engineer may need to dissipate the excess heat due to the motor inefficiencies. Engineering today is about systems thinking, which can be enhanced by parametric thinking, considering how the one impacts the many. I want to highlight again a common mistake that many engineers make is not understanding that a revolution is not a radius, is not a radian. So the power, this equation here at the end of the slide, the power P dot is equal to mu times Ri cubed times omega squared divided by the gap distance times 2 pi L. So this is nothing more than the product of the torque times omega naught, but these are the parameters that one can see that impacts the power. Now let's throw this into a spreadsheet and understand visually or graphically what my solution is telling me. So here we have on the y-axis the torque, and on the x-axis we have the gap, R0 subtract R sub I. I have a speed of 10 RPM. I know that the length is equal to 5 inches, and I have a fluid viscosity of 2.54 pounds per second per foot squared. And all we're doing is simply, as we look at the distance, or no, as we look at the gap, we can see indeed that as the gap gets smaller and smaller and smaller, the torque necessary to overcome shear, the torque necessary to overcome drag increases significantly for extremely small values of the gap. So our torque increases, and also the power necessary to turn my motor also increases as well. So it's good to understand the torque and the power, because ultimately, as mechanical engineers, we ultimately have to size the motor necessary to turn the shaft, to turn the cylinder in the gap, and the power influences the size of my battery pack, and the current draw from my battery pack as well. And that concludes our discussion today, and thank you very much.